All right. Welcome again to our eighth video in the series. So we're going to be kind of what we've been doing so far is we've been kind of covering the basics of control systems, where we looked at essentially like a simple kind of like the transfer function analysis, and we looked at Fourier, and then the Laplace equivalent, and then we started building up from there, and then we revised some of the concepts on using state space and then state space control. And then we got a little bit more familiar. And then we switched gears a little bit where we started talking about probability. And then we kind of got back in track or on track, and where we kind of like converted the probability into what's known as a random variable. And then the next step we took was essentially random process. So we'll just catch up on the concept of random process and noise really quickly in this video. And then once we do that, we will talk about what's known as filtering. So filtering is when essentially concepts you can think about having a sieve, and then you pour, if you're drinking tea, maybe you're from England, and then what happens is you have the tea bag, which kind of holds onto the bigger particles that you don't really want in your tea, and then you have the stuff that you want kind of gets filtered through. So that's kind of like what the basic concept of filtering is. Rather than it being particles, what we are dealing here is kind of like limiting the frequency. So we say, I'm interested only in this particular frequency, but the noise itself could be pretty large. And then I want to maybe get rid of this part of the noise in the frequency domain. And we'll talk about how we can actually do it. So this will be the normal filtering. So we're not yet into Kalman filtering, which is maybe a slightly better way of doing filtering, but it's still like the normal or traditional filtering is still pretty useful. So we'll cover that in this particular video. So with that, so these are going to be the topics that we're going to be looking at. So we are learning objectives are going to be introduction to filtering, and then we look at designing filters. In that we look at analog filters, basic concept of them, how you would actually implement what's known as a low pass filter, and then we'll look at Butterworth, Chebyshev I, Chebyshev II, elliptical filter, and then finally we'll conclude with some discussion on digital filtering. So all of the filters that we have here could potentially be implemented in the discrete time domain, but then we'll talk a little bit more in terms of example and how the things work out. So let's do a quick recap of some of the concepts we covered before. We talked about what's known as a stochastic process. So it's going to be a continuous random variable that also varies with time. So an example would be kind of the temperature in the room, where it can kind of like change, but then it is a continuous process and then it changes over time. So you could do kind of like a discrete sampling of the temperature, which would essentially become a discrete time process. So this process or noise could either be continuous or discrete in time. We have some aggregate parameters of the random process. We call it the mean, which is the average, or the expected value is also another way to think about the average. What that means is if I collect enough number of samples, what will kind of be the effective value or the mean of the thing, that's called as a mean. And we also have what's known as a covariance, which is a measure of the distribution of the noise. So the mean and covariance do not change. We call the process to be wide sense stationary. If the process itself doesn't change, it's called as a strict sense stationary. Generally, we'll be dealing with wide sense stationary. So a strict sense stationary process is also going to be a wide sense stationary or a WSS process. The other topic you would typically hear about when we are discussing noise, particularly in the context of Kalman filtering, is that the noise is termed as a Gaussian white noise. So what do we mean by that? Is if the process or noise X is said to be white, if the value of the process or the noise at time instant t1, denoted by x of t1, is independent of the value at x of t2. So what that means is if I tell you what the current value of a particular variable is right now, there is no way of you calculating what the value is going to be at the next time instant. So if you think about the temperature example, if I tell you the temperature is say 37 degrees right now, the next second it's likely to be 37 degrees, right? So then the temperature isn't really a white noise process. But there could be other process where, instance, if I take and then I'm measuring, say, for instance, there is a whoosh noise coming, and then I at each instant sample that noise, and then I tell you at this instant the voltage is say zero point 0.1 millivolts, and then if I ask you what's going to be the value in say 10 seconds, there isn't really any way of you to actually tell that value. So in that case, the noise is going to be white, where the noise can kind of like the couple of ways of thinking about it. So one way is that the value is completely independent in terms of the time. But then if you switch and then think about the frequency, that basically means that the frequency can be like it just spread over the frequency response kind of like spread over the entire spectrum. That means like it can kind of like switch arbitrarily from one value to the other, and then it can because of that means that the frequency could potentially be infinite, and then it can take any frequency within that range, right, from 0 to infinite. So the next thing is what's known as a Gaussian noise, Gaussian process. So what that means is if I calculate, if I just look at the noise at one time instant, then I expect the distribution to be Gaussian. So then that is known as a Gaussian process. So at any time instant t, the likely outcome has a probability distribution which is given by the Gaussian distribution. So then we typically want to get rid of this noise. So what actually happens is if you think about implementing a control system, and then you have say a feedback loop, and then any noise that gets into your system is going to go into your feedback, and based on how well you design it, so if you have a very high gain, so what will happen is the noise gets amplified, and then your system might just be jittering all over the place, and then that's not great, both from the performance perspective, and then you're going to be spending a lot of energy on kind of like the chatter effect, and you can also wear out a lot of the mechanisms. So in all of those aspects, the noise isn't going to be great. And the first we are going to be looking at, in, at least today, is kind of doing a frequency cutoff or frequency-based filtering of our noise. So we will now look at some of the basic types of filtering or filters that we would typically use. And so you're going to have these laid out here, and then we kind of describe these analog filters. So the same concept actually applies in the discrete time or a digital filter as well, but it's just easier to draw in this particular case. So typically we don't want the filter to have kind of too high of a gain. So you don't want to connect your device to the filter and then it kind of amplifies the signal 10 times. So that's not really the function of the filter. So typically we're going to assume that the gain is going to be, the maximum gain is around 1. There will be some variation, which we typically don't want. But nonetheless, we're going to always plot it from the gain of 0 to 1. So if you have a gain of 0, that means that the signal, that region, the frequency domain is completely quote unquote killed, or it's completely attenuated, right? So this is what is allowed to pass through, and then there is a region that's blocked. And then based on which set of frequencies are allowed and which are blocked, we would give different names for the filter. So the first filter that we're going to be looking at is what's known as a low pass filter. An ideal low pass filter allows all the frequencies below a particular cutoff frequency and then blocks or completely attenuates all of the frequency above the cutoff frequency. So if I wanted to graphically plot it, use this one for the low pass filter. So my response is going to look something like this, where the frequency below this cutoff frequency is all allowed to pass through, and then the frequency above this is the gain of the filter is going to be 0. So what will happen is if I pass any signal through this filter, because the gain in this region is going to be 1, all of those frequencies are allowed to pass through. So for instance, if I had a combination of sine, and then there is one sine with this frequency, another sine with this frequency, the output signal will only contain sine with less than fc. So fc would be any frequency, the cutoff frequency that you choose as a designer. So if you say design a 10 hertz filter, then your fc is going to be 10 hertz. So the next one is the flip or the flipped version of our low pass filter, which is the high pass filter, sorry. So this region is going to be known as the pass band, where the frequencies are allowed, and then this region is known as the stop band, or the region that's blocked. So the next is the ideal high pass filter. So the way that it works is kind of the opposite of this. So if I create a plot, it's going to look like this. So what it does is it blocks all of the frequencies below the cutoff frequency, and then it allows all of the frequencies larger than the cutoff frequency. So a typical example where you would use this is if you have a gyroscope in your device. What's going to happen is it's going to have a small drift, and then what you can potentially do is use a high pass or a high pass filter to cut off some of the DC bias or kind of the drift in your signal, and then allow only the high frequency component to be allowed to pass through. So we look at few different variations. So you can potentially think about, so you've looked at kind of allowing all the frequencies below a particular value, and then we looked at all the frequencies above a particular value. So you can kind of do the kind of like combine the two, where you allow only in a particular region. So that's known as a band pass filter. The band pass filter would only allow signals between a FL and a FH. So if I draw the schematic, it's going to look something like this, where the frequency in this region is allowed to pass through, and then it blocks all the frequencies here, and then blocks all the frequencies here. We can do what's known as a notch filter, which is again the inverse of the band pass filter. So a notch filter would look something like this. A typical example of a notch filter would be if you're in North America, so you have a 60 hertz signal, electrical signal, and then you would expect a lot of the component from your 60 hertz and a lot of its harmonics to show up on your signal. And then if you know that your controller doesn't really have any need for it, you can potentially use a 60 hertz notch filter where you block out that particular frequency. Again, you need to be careful that if your system does respond to that 60 hertz value, then you might actually need that signal. But if you know that your signal is always going to be here or here, then you can potentially use a notch filter. And then you can also use a notch filter, for instance, in the microphone, where you can cut off the 60 hertz whine or the hum, and then that could potentially improve your outputs. So now let's look at how you can practically implement this particular filter. So we'll pick just the low pass filter as example. So here conceptually, if you think about an input signal coming into this circuit over here, it's an RC circuit where R is a resistance and C is a capacitance over here, and they're connected in series. And then you take the output with respect to the capacitor, and this is the zero reference for your circuit or the ground. So if you imagine a very high frequency coming in, what's going to happen is that the capacitance is going to act as a short circuit because it's going to allow the higher frequency to just pass through. That means that the voltage here is going to be zero. So the output response of the capacitor or the output response to the circuit here is going to be zero. If I have a very low frequency, say an example like apply a DC 1 volt signal, then my capacitance or capacitor is just going to charge up, and I would see that 1 volt in my output. So at very low frequency, my output is equal to my input. At very high frequency, my output is going to be zero. This can be represented in the Laplace form as 1 over RCS plus 1. And then this, if you actually draw the frequency, and then I put the frequency in dB, which is 20 log base 10 of my magnitude of my signal. And then this is frequency. So if I plot it in the log scale, I'd get a response which looks like this. So typically we can say I'm going to pick this, since this varies continuously, I could pick like a 3 dB point over here and then call that my cutoff frequency of my circuit. And then this would be, so if I give the frequency in radians, then and you can convert between radians and hertz using this particular formula over here. So what I can actually do is I can actually make this transition faster. Right now, this is going to be 20 dB per decade because I have only one pole over here. So if I add more of those, I can actually make it faster. And this is how we can actually implement a particular frequencies or the filter. So you can never get the sharp transition that we had in the previous page, which is the ideal kind of like a step where you're completely blocking off some frequencies and completely allowing some other frequency. So typically your attenuation is going to look more like the figure I have at the bottom. I know this looks like a squiggly line I just drew without having my morning coffee, but this kind of nonetheless allows and then kind of like allows us to pick some and highlight some of the features over here. So here the frequency, or rather if I apply and then I'm going to get a minus 20 dB per decade slope on my Bode response, and then I can potentially add more poles and zeros and then affect how quickly the transition is going to occur. So typically we don't want to wait for a very high frequency, so you don't want to wait for a few decades in terms of your frequency response. What we're mainly looking at is when looking at filters, we look at the linear frequency. So if you did it in the linear scale, what will typically happen is you're going to have a transition. So here, this region is known as the pass frequency. So you're going to allow all the frequency in this region over here. And the frequency response actually reaches some lower cutoff frequency. And then we'll call that the stop frequency, right? So depending on how you choose your transfer function, you may or may not have these ripples over here. Similarly, you may or may not have the ripples in the top. But in general, we're going to assume based on the combination of the poles and zeros of your transfer function, you do end up with some ripples over here. So labeling few of the other things. So the total ripples here, which is known as the ripple in the pass region, is known as the pass ripple. We can denote that by R sub P. Similarly, we can have a ripple, but rather than measure the ripple here, just in this region, which is not very useful, what we measure instead is the minimum attenuation that we have. We call this the stop attenuation. So what that means is once my frequency crosses my stop frequency, none of the frequencies are going to have a gain larger than my stop attenuation, or the stop attenuation is the minimum attenuation I get in the stop region of the frequency or in the stop band. So since this is going to be called the pass band, this will be the stop band of my frequency response. Again, I repeat myself. So you're going to have some ripples over here. This is going to be dictated by the poles and zeros of your transfer function. See, poles and zeros of your transfer function. And you can actually control this, which is what we do. And there are standard ways to control this. But what we are mainly looking for is we would have some amount of ripples here, which is known as the pass ripple. And then what we're going to have is we're going to have some attenuation here. Again, rather than look at the size of the ripple, what we're rather interested in is the minimum attenuation that we get in this region over here. There is going to be a small difference between the pass frequency, which is over here, and then the stop frequency over here. And this is going to be kind of the transition region in your filter. So the first filter we're going to be looking at is known as the Butterworth filter. So some characteristics of the Butterworth is that it has no ripples in the pass band or the stop band. So the filter is sometimes referred to as the maximally flat filter. And then it's going to have the downside is that it's going to have a relatively wide transition zone. We have the figure in the next page, so I'll discuss a little bit more about what I mean by this. But the poles of the filter is given by the equation here, minus sine 2k minus 1 pi by 2n plus j cos 2k minus 1 pi by 2n times omega c, where omega c will be cutoff frequency, and then for k equal to 1 through n, where n is known as the order of the filter. So I have those just coming up in the next page, so you can note that down. So the response doesn't have any bumps or ripples. So what do I mean by that? Is if I have a plot, or if I try to plot this frequency, if I plot the frequency in the gain in dB, and the frequency in hertz or radians per second over here, I'm going to get a response similar to here. Just keep in mind that the response seems to flatten out here because I'm looking at the frequency in the linear scale. So what I do by cutoff is I measure minus 3 dB point, and this is going to be my cutoff frequency over here. So this drop off is going to be minus 20 dB per decade times the order of the filter, but that's going to be on a log scale. But if you look at the linear filter, the drop off would appear to kind of like flatten out, because if you imagine the frequency gets more clustered as you increase on a log scale. So in MATLAB, you'd use the command b comma a is equal to butter nwc f type and then s. So s is used for denoting it's going to be a continuous type. So f is the filter type, which is going to be low, band pass, high, or stop. So this is actually going to be a string input. So you put this within single quotes. N is going to be the order of the filter. That's also going to denote the drop off here. WC is the cutoff frequency. If you have a band pass filter, you would send in two elements, and then B, comma A will be the denominator and numerator of your polynomial, and then you can actually use different combinations to, for instance, you can actually write this in ZPK form in terms of the zeros, poles, and gains. So ZPK would be the zeros, poles, and gains of the transfer function respectively. We can also do it as a comma b c comma d is equal to butter the same thing, where a b c d will be the state space matrices of your filter. It should be noted that once we fix the order, we can't really control the stop band frequency or the width of the transition period. So all of that is entirely determined by the order of the filter that you choose. Okay, so let's look at an example. So the design problem is to design a first, second, third order Butterworth filter with a cutoff frequency of 1 Hertz using MATLAB. Then we're going to examine the zeros and poles of the transfer functions as well as the attenuation or the filter gain from 0 to 10 Hertz on a linear scale. So again, so if you recall, so we go back a few slides. So the actual formula is over here. So we're going to use this over here. So b comma a is equal to butter n w c f type and s. So we have everything that we need. So essentially b comma a is going to be the denominator and the numerator. The other way to do it is you can use the ZPK representation, which will give us the zeros and poles. We have the WC, so that's the cutoff frequency. So we're given the cutoff frequency in Hertz, so MATLAB would require us to convert that in radians per second. And then F type is going to be low pass filter. So again, recall it's a string that we put in. And then because it's a continuous time filter, we are going to use our add S at the end. So this is what we're going to do in MATLAB over here. So let's go back to the slide over here. And so let's do that. So I'm going to open up MATLAB, which is over here. And then I'm going to do something different. So I'm going to do something known as a live script, which is going to create a new blank live script. So this is a slight variation of the MATLAB scripts, which allows you to run all of your commands and then as well as paste the outputs directly into the screen or as we go along. You can kind of like look at it and do a few things over here. So you can either, first things first, is there are a few additional options that show up over here. So in terms of section break, task, code, and so on, and then control and so on. So essentially, you can kind of add, like, so within this, you can add like numerical indicators, drop-down menu, and then assign variables. So right now, we're not going to use any of these options. So what I am going to do is switch between this, which is called as text, and then this part code, which is currently already selected. And then when I look at the examples for the next filters, I'll create a new section so that I can run only one particular section of the code. The other thing is, if I look at the output over here, so it says to show whether I want to show the output on the right. So that's my output is going to show up as figures over here. If I click here, all of my outputs are going to go show up inline, and then here I can hide the code. So let's save this. So we're going to call this, say this is week 08, and then we'll call filter design. And then it's going to show or save it with an MLX extension. You can actually export this to a normal script and actually extract the command, and you can actually potentially open a normal script using the live script or live script editor, and then have it run commands inline. So I'll show you why I actually did this. So I'm going to first, what I'm going to do is copy my problem. So we're going to be doing the Butterworth filter, right? So let's do this. I'm going to copy the text that I had and then do here. And then here, actually, I need to switch this to a text. Let's cut. So I'm going to go to text mode, paste this guy. So I can actually give like nicer headings and so on. So we'll call this maybe filter design, and then maybe make this the title. So I'm going to drop down and select this as title. So we'll make this as title. So if you want, you can kind of center the title. So we put it in the middle. So this is going to be my first section. So I'll call this header. I'll call this maybe heading 1. It's going to be the Butterworth filter, and this is going to be my problem statement. Let's make it a little bit nicer. So this is going to be my problem statement, and then I can do the solution below here. So we are going to do the plots in a particular range. So let's type in things we know. So let's make it a little bit nicer. So this one, so I know my cutoff frequency is going to be 1 Hz. So maybe I'll call this FC is equal to 1. And then this is, you can give it labels if you want. In hertz. So we would eventually need to convert this into radians per second. So the way we go from frequency in hertz to radians per second is you multiply by 2 times pi times fc. And so this will be in radians per second. And then we can save this. So a good practice would be to save it as frequently as possible. So then, so we are basically going to be designing first, second, and third order filter, right? So let's do that. So then we switch back to text. So it's Alt Enter and then Alt Enter switches. So let's do Alt Enter. So then we'll call this first order. So we can change this to say like heading 2 just to make it a little bit nicer. So this is going to be my first order. Save this again. So I'm going to do, just to make things easier, so what I'm going to do is, since it's first order, so I'm going to define my n to be 1 because it's first order. And since we are interested in looking at the zeros poles, I'm going to use the ZPK representation. So I'm going to go ZP comma K, and then this is equal to butter. And then if you recall, I'm going to have the order here, the cutoff frequency, and then I'm going to do type. Because I'm going a low pass filter, the type is default, but if you want, you can include the type as low pass over here, but I'm going to skip that. So and then say S, and then close this. And then now we have the ZPK, So we can print all of these. So we want to make it nicer. So we can just say display and then give the name. So there's going to be a Butterworth, right? So we can just say Butterworth filter and then order 1. It's not strictly needed. So and then we can just display the ZPK, display Z, display P, display K. Then save this. So this, we need to make sure this is actually in code rather than text. So let's just change that and then save it again. And then now if I run, it should output, provide my output. So it's just saying it's trying to run this part right now. And then it says unrecognized R. Let's run this again. So then it says first order, and then it has a 0 at this value, and then P poll at this value. So you can actually add more text and then make the whole display nicer. So let's maybe do that. And then maybe display poll. So, and then we do for K, display and then display K, and then we can save this. And then I can run this. So right now it says 0, there's empty, so there's nothing there. And then we have poll is minus 6.2832, and the K is 6.2832. So if you notice, this is actually very close. This is actually equal to the 2 pi times FC, so it'll be equal to omega C if you wanted to actually compare this. So we have all of these. So we have done this plot, we've done this, and then now we have to calculate the essentially the frequency response of this particular system. So now, in order to plot the frequency response, so what we need to do is we have to generate the frequency values. So there are different ways you can do it. So you can kind of calculate the Bode plot, and then from that you can calculate the Bode response. And then MATLAB actually offers few easier tools that we are going to use here. So because I'm going to be using the same frequency to compare, so I'm going to maybe define the frequencies that I need over here. So I'll just call this F, maybe F plot. And then I'm going to go 0, 0.01 to 10. So all of these are going to be in hertz, and save this. And then we're going to do one of those commands to actually convert this to frequencies. So we're going to call this maybe like a gain. And then we call this, we use the command called freaks. So this says it's going to plot the frequency response of the analog filter. So for this, it needs B, comma, A, comma. W is the frequency range. So this is going to be 2 times pi times F plot. So if you note, we actually don't have the B and the A for the frequencies, which are going to be the numerator and the denominator polynomial, right? So then we use another command in MATLAB. So Z comma A would be equal to, so we're going from ZP to TF. So you also have the other option, ZP to state space, and all of the other options, but we now need it in transfer function form. And then so now we have Z comma P comma K. Then hit enter and save. And then next, since we have the plots, we're going to plot this. And then we'll call this, so we're going to plot the F plot in hertz. And then we're going to go magnitude. And then, so there is a magnitude to dB, which I can actually use. And so there's a function. And then I'm going to pass or send it the absolute values of my gain. And so there's this. Then we have all of this. And then let's try running and then see what actually happens. It's actually running this particular command. So it's going to actually create the plot. And then because I have it as side by side, it's going to add that plot over here. So this is my frequency response. And then if I wanted to make the plot nicer, I can add the X and the Y label. So we can call it X label. So this is going to be frequency in Hertz, and then the Y label, and then this is going to be gain in dB. And so we don't really have a legend. What we can potentially do is have kind of like a running legend, and then so legend we're going to use this form thing over here. So we just call this maybe this is Butterworth order, right? So we'll just call this butter n equal to 1, and then so you will shortly see why I'm actually using kind of this representation over here. So this actually allows you to store strings of different lengths. So this isn't really an array, so it actually is kind of a different data format within MATLAB. So this format is known as cells. So what it allows you to do is actually store different kind of data sets and potentially strings of different lengths. And then if you look at the help for legend, it says it actually accepts a list of shells, cells, and then that can be saved. All right, so the next problem is to do a second order. So you can actually type out the whole thing, but since you probably know that I'm lazy, what I'm going to do is just like copy this and then paste it below over here. So now there's actually second order. So we'll change this second order. So to get second order, we change n to 2. This remains the same. This just to print our title, make it nicer. So it's going to be order 2. Zeros, poles, case, all of this remains same. And then this is going to be n equal to 2. So if I did a regular plot, it's going to overwrite the previous plot. So what I'm going to do is say hold on, and then hold off, and then save. And then if we run this, it's going to do the two different filters and then actually compare the results over here. So it just says butter, since we saved it in the same place, it's overwriting. So now let's fix that mistake. And so now we have the comparison between Butterworth 1 and 2. So you'll notice that the second order seems to have a steeper roll-off compared to the first order. So we're going to extend this and then create the third order. So again, I'm going to copy and then paste. So this is going to be third. And then so n is equal to 3. This is saved. So the title or whatever is printed gets changed. And then we'll change this to 3. We change this to 3. Save and then run. So now it's comparing the 3 responses, and then you notice that obviously as you increase the filter order, the drop off becomes much steeper. And then notice all of these guys actually cross this point over here. So if we measure, so this is actually minus 3 dB. So this is minus 10, and then this is minus 5. So this is the minus 3 dB point. And then so all of the frequencies would be 1 Hertz because we chose the cutoff frequency to be 1 Hertz. So if you had a different cutoff frequency, so obviously this point would be different. So the other thing you'll notice that as you increase the order, it actually gets more flat in the pass region. So that's another nice thing that is happening here. The downside to increase in the order obviously is that you're going to add complexity to your filter. So the Butterworth command itself doesn't have too much control. So you just have to give it the order, and then it's going to give you the frequency response, and there's just like one response that comes out. Actually, it gives you a particular combination of filter, and there's only one response that's going to come out, and then you can't really tune the other parameters that you want to do. So if you instead wanted to design a filter where you say, I want maybe like a particular characteristic in terms of the cutoff, the pass band frequency, the stop band frequency, and the ripples, and so on, then you would use this function, which is spelled Buttord. So it's kind of essentially short form for Butterworth order. And so what this does is it's a design tool that allows you to calculate the order and kind of the natural frequency of your filter based on the characteristics that you want. So in this, what you would do is, if you assume this is the 0 dB point, and then if I draw a characteristic where this is going to be the pass frequency, this is going to be the stop frequency, then I'm going to get a characteristic that looks something like this. The region here, this is going to be the pass ripple. So essentially, it's going to adjust this pass frequency so that, so if I set this to say 3 dB, then it'll ensure that it passes through this point. If I say it's like 10 dB, then it can kind of like adjust the frequency based on it. And then the other thing it does is it ensures that the line passes through the stop frequency and then the stop attenuation that I want. So this is going to be the attenuation, and then here it's going to be a continuous time. So let's look at an example here. So you're going to design a Butterworth filter with a cutoff frequency of 1 Hz and a minimum attenuation of 20 dB at 4 Hz with a pass ripple of less than 0.5 dB. And then again, we're going to examine the zeros and poles of this particular design, and then kind of like compare it, if you want, with the previous design. So for that, I'm going to pull my MATLAB screen again. So I'm going to kind of like be lazy and then kind of just like reuse this term over here. Just like maybe let's copy this, since I'm going to be reusing most of this. So maybe let's copy, and then we'll call this design. And we have the problem statement. So maybe now would be a good time to actually copy the problem statement. So we'll paste the problem statement. It says design a Butterworth filter, 1 Hz, blah, 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 all of this. Since I don't know the order over here, so I'm going to use the command that I had. So here I'm going to comment this out since I don't know the order. And then we'll do n, comma wn would be equal to Buttord. And then here I'm going to have WC, which is the pass, or WP. And then it says WS, comma ripple, and then ripple stop. And then there's going to be a continuous time. So now let's define all of these terms. So WP is the pass frequency. So I wanted that to be about 1 Hz here. So there's going to be 2 times pi times 1. I'm going to directly do it in radians. My W stop is going to be 2 times pi times, go back here, it says 4, and then it says with the minimum attenuation, so the stop attenuation is 20, and then the ripple in the pass is 0.5. And then I can as well copy all of these here, but I can do this here. So Butterworth filter, maybe change this. So once I do that, I'll use the N and the WN in the actual design. So this is going to be WC. And then let's just display N. WC. So we print all of these values just so we know how the design actually looks. And we do the B and the A, and then we're going to essentially copy that. So we'll change this. This is going to be legend 4. And then butter design, legend, and all of it. and then we can just run this and then see what happens. It's going to actually run the whole set of commands. So if I didn't want to do that, what I would actually do is, um, um, so what I could have potentially done is just created sections and then just run that. So here's the design. So that's the violet. So I basically had a design with 3, and then this is 11. So the reason is based on my design. Um, this is what I get. So at 4 hertz, I get about 20 dB of gain, and so on and so forth. So it's basically gotten me the design. So it's very similar to the third order, just that it seems to be shifted a little bit. So moving on. So the next filter we're going to be looking at is known as the Chebyshev filter design 1. So the advantage is it basically has a smaller transition for the same order, but what you sacrifice is you tend to have a little bit more ripples. So this one, the first Chebyshev type 1, is made by actually moving the poles of the Butterworth filter to the right and scaling the real and imaginary part. So we aren't actually going to do the formulation, just that we're going to run and then kind of do the same thing we did before and then look at the formulation. But before that, we just make few notes. So the way we do the design is we do similarly, we can do B comma A or ZPK or ABCD, and then we can say that is equal to CHEBY1, and then here we specify the order, the pass ripple, the pass frequency type, and then S. If you wanted to do the design, we have this comma pass would be CHEB1 ORD, and then we give WP, WS, RP, RS, and S, and then substitute these values into here. So here, all of the terms have been same as defined before. So N is the order, RP is a pass ripple, WP is the fast frequency, and then here WS is the stop frequency, and then RS is the stop ripple. So we are going to design a first and a third order Chebyshev type 1 filter with a pass frequency of 1 hertz for ripples of 0.5 dB and 0.3 dB. So essentially we're doing four designs. So we're going to go first order with 0.5 dB, first order with 3 dB, third order with 0.5, and third order with 3 dB. So essentially 4 designs that we do. And then we're going to examine the zeros and poles of the transfer function as well as the attenuation gain. And then we will compare all of these and then see how that actually looks. So what we're going to do is do something similar. So we're going to create a new filter design, or we can actually create another section over here. So we can just, maybe I can just create everything in the same file so it makes it easier. So we'll call this Chevy type 1. This is going to be, maybe make it nicer. Save this. And then I'm going to copy paste the statement that we had. So let's paste this problem. Design this and then solution. Save. So here's what we're going to do. So let's do the first. So we're going to basically do, this is going to be the first order. And then with the ripple of 0.5. And then we want this to be, actually let's do a section break here. And then we want this to be code. So the reason I did a section break is I can actually run this separately. So I'm going to do the code. So if you want, you can clear everything here. And let's do the same thing. So my pass frequency here is in radians per second is going to be 2 pi. And then I have 1. And then my ripple in the pass region is going to be 0.5 for the first case. So let's do that. And I'm going to do the, since I know I'm going to be plotting, so let's do the f plot is 0 colon 0.01 colon 10. And then we have cleared the legend and all of the other things that we need. So we have define all of this. And then let's do the plots. So we're going to go, since we defined, we're going to do the first order. So there's going to be n equal to 1. And then let's do the ZPK version, Z, comma, P, comma, K. And then if I maybe 1, and then it's going to ask what I need, N, RP, WP, F type I can ignore because it's going to be low pass. If I want it, I can actually say low pass as well. And then now I'm going to skip the semicolon so that it just prints everything in terms of ZPK. And then once I do that, I'm going to do the same thing. Since I'm going to do the similar plot in terms of the frequency, I'm going to convert this to ZP to TF. And then I'm going to go Z, comma, P, comma, K. And then I'm going to go frequency again. So that's going to be the H or the gain. So that part we can just copy from here. So we are not going to do the hold here because this is kind of like new one. So we'll probably need to do this. Frequency, and then this is going to be of 1. So Butterworth n equal to 1. This is the pass frequency of 0.5, right? Ripple pass is 0.5. Save, and then we run this section. So it says Z is empty, P is 70, and K is this. So it's done the plot for the newer Butterworth filter. So now we're going to copy paste and then do first order, and then we have the ripple 5 here, so we can kind of like redo the ripple for the other case, and then maybe you can just get rid of the stuff we don't need. So ripple, so I'm going to do the next one as I want a 3 dB. So let's do ripple of 3 dB. So this ripple is going to be 3. So I've actually defined this guy already, the cutoff frequency, so I probably don't need to define it again. And then this is defined as well. So let's save and then just change this text. It's 3 dB, and then this is legend 2. And since we're here, might as well redo and then create all of the other stuff as well, right? So I'm going to do that. So now you're looking at a order 3, right? So let's do ripple this. Then we probably need one more. N equal to 3. So we do n equal to 3. N equal to 3. And then this ripple is 0.5. So this is 0.5. And then this is n equal to 3, ripple of 0.5. So this is the third one. And this is the fourth one. So here n equal to 3. And then ripples is equal to 3 as well. So the other thing we need to do is get rid of the clear all statement and then make sure we have the hold on and hold off here. Hold on. So maybe just are lazy, so we just copy this part and then replace this plot. And then we don't want the clear. Same thing for the previous one. Then we save, and then we can run this section alone by run. So it's saying what's happening here. And then here are the plots. I think it looks like it's running the whole problem. And then here is the Butterworth calculation. So I should have run, if you run sections, it'll run only this part of the code. So, but this gives us a good opportunity. So once you save this, to kind of like quickly compare how the plots actually look. So actually can make this bigger. So notice that the Butterworth, this all of it was like reasonably flat. And then here, notice that there is, based on the ripples that you allow, so this is allowed 3 dB of ripples. So then there is a bounce up to minus 3 dB over here. And then all of it, you're not actually controlling the stop frequency of any kind. So we can actually do that using the design framework that we mentioned. So some observations on the Chebyshev version 1. So if we increase the order, so obviously the roll-off is faster. So just pull this back. So if I compare the same ripples, 0.5 and 0.5 over here, between the blue line and the yellow line, so notice that obviously if I increase the order, the roll-off is faster. So that's known. So if we allow for higher ripple, so we get more ripples um, uh, in the pass band. So that's actually obviously expected. And then the other thing is it also improves the attenuation, but not as much as increasing the order. So if we compare the lines with the same order, so n equal to 1 with 0.5 and 0.3 dB ripple, so the 3 dB actually has a slightly faster roll off. So the line's always lower. Similarly, if we compare n equal to 3, 0.5 and 3 dB, so the 3 dB actually is below, and so it basically offers higher attenuation for the same frequency. So so the easiest way or the better way to get higher attenuation is to obviously increase the order and then have maybe like a small ripple here. The other option is if you want to fix the order, increasing the order increases the complexity of the filter. What if you can tolerate a higher ripple in the pass band, it allows you to actually get a slightly better stop band performance. So next, we're going to look at what's known as Chebyshev type 2 filter. It's also known as an inverse Chebyshev filter. So this requires slightly more component. So it has no ripples, but it has a slightly steeper roll-off. The difference is in the type 2 filter, we are actually controlling the stop band characteristics of the Chebyshev filter rather than the pass band characteristic. So as such, the way it'll look is we have B, comma A, ZPK or ABCD. So based on what you have on your left-hand side, it'll output the corresponding configuration of the filter. So then it has Chebyshev II, and then you're going to have N, RS. So RS, if you recall, is the stop attenuation or the minimum attenuation of the stop inside the stop band. WS is the stop band frequency. FS is the type, and S is to denote it's a continuous time. Again, so all of these notations are the same as we defined before. So we would use CHEB2ORD, which is for the Chebyshev order to design. So here we can get the order and the stop band frequency. If we send it the WP, the pass band frequency, WS, the stop frequency, RP, the pass ripple, and RS, the stop ripple. Again, so you can just type in help for this particular command in MATLAB or doc, and then it gives you more information regarding this particular command. So we're going to do the design here. So we're going to design a first and a third order Chebyshev 2 filter with a stop frequency of 1 Hz with a minimum attenuation of 20 at 40 dB. And then we're going to examine the zeros and poles. So I'm going to again pull up MATLAB, and we will copy this and then do the same thing that we did before. So again, so we're going to copy some of this. We'll do a section break, and then this is going to be Chevy type 2, and then let's copy paste the problem statement. So I'm copying and then paste it guy here. So we're going to design a first and third order Chebyshev filter with a stop frequency of 1 Hz, minimum attenuation, blah blah blah. So again, I'm a little bit lazy, so I'm going to copy the first order here. And then we'll make the design changes to this code over here. So this is first order ripple. So there's going to be stop RS of 20 and clear all. So we're interested in the stop. So we'll do WS. RS will be 20. And then F plot, we keep it as is. And then we're designing Chebyshev II. And so we're going to pass it the order and then RS and then WS and then type and then continuous. And then we do this, and then we plot the letter. So this is going to be Chevy. This is going to be Chevy type 2. And this is going to be order and then the stop of 20 dB. So let's just run this and see how it looks. So it's printing out the K's and zeros, and we'll see how the plot actually looks. So you notice that it kind of just so the cutoff frequency is a little bit on the low side, and then this is what we get. So in the interest of time, what I'm going to do is actually, rather than copy paste, I'm going to show the final result. So here is what we get. So I'm going to pull the screen, make it a little bit bigger. So obviously what it's trying to do is once I give the stop frequency, which is about 1 Hertz, is going to be here. For the blue, it says at 1 Hertz, it needs to be about minus 20 dB. So that's what it's trying to do. And then for the red, it needs to be minus 40 dB. So that's what it's done here. And then it just stays below. So once we increase the order, things get a little bit more interesting. So where it's able to add and few more things. So you'll actually notice if I scroll up that in top of the gain, so it's actually adding some zeros to the system response. And what the zeros allows you to do is make the response a little bit faster, but then it comes back up. But I'm actually ensuring that the stop cap or the stop band attenuation is maintained, but just that I can give a much quicker roll off and kind of to reach that particular value. Just that I can't actually control the pass band over here without changing the order. So let's note down those observations. So we can control the stop band. We add zeros to make the transition faster, particularly if we increase the order. Typically, if the order of n, we can add up to n minus 1 zeros, and then we can't actually control the pass band on the filter. So the next one we're going to be looking at is what's known as the elliptical filter. So the advantage is it can potentially offer much sharper transition at the expense of higher ripple. So again, we're going to B comma A or ZPK or ABCD would be equal to ELLIP, and then N is the order, RP is the pass ripple, RS is the stop ripple, WP is the pass frequency, and then filter type, and S for continuous design. If you wanted a design, we do ELLIP ORT, which gives you the minimum order that is acceptable. Again, so the problem is very similar. So we're going to design a first and third order elliptical filter with 0.5 and 3 dB with a minimum attenuation of 40 dB here. And then we will do the design. Again, in the interest of time, so I'm just going to pull, and then I've done all of these results over here. and then we copy this, and then this is the results of the elliptical filter. So you'll notice again, it does have a much sharper transition than we noticed before. Just that if you zoom in closer over here, so it seems it has a little bit few more ripples in the pass band, and it just makes the whole design a little bit more complicated. Again, as a designer, you would need to kind of like do a trade-off between kind of like an acceptable ripple and then how quickly you want the transition to occur. So generally, you would kind of like prefer to use a Butterworth filter or maybe a Chebyshev order 1, but Butterworth tends to be most preferred because it has a fairly flat characteristic in the pass frequency range. So now we come to the last topic for this video, which is going to be digital filters. So essentially all of the filters we discussed, Butterworth, Chebyshev II, elliptical filter, can be implemented as digital filter. So you can actually look at the help, but the main idea is that if you drop the S at the very end, then the design just becomes a digital filter. Just a quick note, the only thing that changes is that if you drop the S, it becomes digital. The cutoff frequency that we pass would be the normalized frequency. So then what we need to do is kind of like divide all the frequencies divided by Fs over 2. So here it doesn't really matter. So you can keep everything either in hertz or in radians per second. So if your sampling frequency is in hertz, then your cutoff frequency is going to be in radians, and then you can divide. So for instance, if I wanted the next example you would see, so if I wanted this example over here, so if the cutoff, so if my say cutoff frequency was 100 hertz and my sampling frequency was 1000 hertz, then you can just do 100 divided by 1000 divided by 2. So you do 100 divided by 500, or which will be 1 over 5, which is what you will pass to your design. So we can actually use few tools to visualize the frequency domain. So the only downside is, so if you think about, you can actually do the design here of the elliptical filter, and then you can compare it with the design for the continuous time filter. So this, I leave it as an exercise for you guys to try and then see how it actually looks. So just a quick comparison. So digital filters are often easier to implement because you're going to do it in code, and then it might be easier to just change few parameters over here rather than swapping out individual RC components and so on. The main disadvantage is most of the signals are going to be starting as analog signals, and it might make sense to actually filter them out, particularly if you're looking at anti-aliasing filters. So what we mean by anti-aliasing is, if you remember, if you're sampling and then your signal is faster than sampling rate, you kind of start to see aliasing effect. If you wanted to get rid of that, what you can actually do is you would need to actually do an unlock filter. So unlock filters also have better amplitude and frequency dynamic range. So an example would be if you're implementing a digital filter, you need to be sampling at least 2 times the signal frequency. But most likely you might have to do like 500 or 5 or 10 times the sampling frequency. So that means if you need a cutoff of say 100 hertz, you would need realistically between 500 to 1000 hertz of sampling, which basically means that if you're only going to be running some code at 100 hertz, what you can potentially do is have an unlock filter which does the anti-aliasing and doing all of the filtering, and then your code can potentially run, or your microprocessor can potentially run at 100 hertz, which will make your design faster. And then if you implement a digital filter, what also happens is you need to have a higher resolution, particularly if you want to resolve both, say, a lower signal amplitude and as well as a higher signal amplitude. So this basically concludes our discussion here. So what we did in this video was we are looking at filter design to kind of like distinguish or kind of send in or accept some frequencies and cut off some other frequencies in our sampling. So essentially we kind of started out by looking at the basic concepts of filtering, where you can potentially do an RC circuit, which will kind of like allow you to take, allow or pass some of the frequencies and kind of like attenuate, kill some of the frequencies. But if you wanted better control in your design, then you can use some of the inbuilt filters. You're always welcome to try to fiddle around with adding multiple RC circuits or maybe an LCR circuit and then see if it actually works. But rather, because you know the characteristics that you need, you would rather use kind of the inbuilt or existing designs of the filter, which makes your design easier, and then you know actually what you're getting, and then all of these formulas have been well tested, and the design is actually much better. So this concludes our video, and thank you for watching, and then see you in the next video.